All right. Welcome back, everyone. So, some announcements to get us started. The next Achieve homework is available. It's all on Chapter 14, which we will continue today and Friday. And then next Wednesday, so a week from today, is the midterm exam. So, that will have all multiple choice questions. It is cumulative. So, we started this semester with Chapter 11, and then it will go through Chapter 14, up to what we cover on Friday. And then I will provide a Scantron, so you just need to bring a calculator and not a writing utensil. You need a pencil. You have to fill in the Scantrons with a pencil. So that means that between now and the midterm, which is next Wednesday, times outside of class that we can meet. I have my office hour tomorrow. It's going to be 2 to 3. We have recitation Friday at 8 online, and then my office hour next Tuesday is at 2 as well. So keep all of that in mind. If you've got questions, those are all good times to ask those questions or just review some content. So yes, we'll continue for chapter 14 today, Friday, and probably Monday, and then the assessment will be Wednesday. Yeah. Yes. So it will be due after, I think the Sunday after or something like that, the learning checks, and I'll add more. I think you only have 11 and 12 up, and I'll add 13 and 14 as well. Yeah.
So what slide is
So it will be what we cover Friday, so I don't know what that's going to be yet. And then today, you may have seen out there, Chem Club is doing a fundraiser. They're selling these Erlenmeyer flasks with their food grade, so you can eat or drink out of them. There's a stopper with a straw, and then they're filled with candy. So those are available just right in the Chem lobby. They're going to sell until 2 p.m. So that's a fundraiser for Chem Club. It's $10 for the Erlenmeyer flask and the candies inside. And then they also have a guessing game for $1, and you can win a free beaker if you guess the correct amount of candy in that. Not a free beaker, I guess it costs $1, but you'd win that if you guess the correct amount of candy. So that's today until 2. You can see them right after class. And then tomorrow is the Women in Science event. So this is at 5:30 p.m. in the ballroom. We have 6 women that work in STEM fields that are coming as panelists, and you will sit at a table with other students and one of the panelists and just be able to talk to them about their career path and what they currently do. We have 6. 5 of them are Detroit Mercy alumni. One of them, I think, is not, but the rest are. So it's a great opportunity. And if you are planning on going, RSVP with the form that you can get with this QR code. I also posted this on Blackboard, so you can get the QR code that way as well. All right, I think that's everything. Questions about anything coming up? Okay, so we're going to continue, of course, with this chapter, but in the first couple sections of this chapter is in the recorded videos, but just to kind of remind ourselves what all of that is about and what chapter 14 is about. It's called chemical kinetics, which is all about the rates of reactions. So there's 2 different reactions shown in these pictures here. One is burning a match. That's a really fast reaction. You can see the match burn down, the chemical reaction take place visually. You can see that happen in like less than a minute. If you have a standard size match, that will completely burn up. But something like iron rusting, forming rust, that takes a lot of time. You wouldn't like stare at a piece of iron and watch it rust, right? Like that would take a lot of time to occur. So that's a much slower reaction. And so that's the reaction rate, how fast a reactant is used up or how fast a product is formed, is what we're discussing in this chapter. So there are a few different factors that influence reaction rates that we reviewed at the end, or I reviewed at the end of the first section. So particle size, concentration of reactants, temperature, how stable or unstable reactants are, and if there is a catalyst. We are currently in a section to describe how the concentration of reactants influences reaction rate. And that picture up there kind of describes this. If you have a lot of reactants present, there's a high concentration, there's a higher probability that molecules will collide with each other, and that collision is necessary for a reaction to occur. The two molecules have to have enough energy to collide and break bonds or form bonds. As a reactant is used up, there's less of that reactant present in the solution, so the reaction rate slows down. And it depends on how much the reaction rate slows down, depends on the reaction order for that particular reactant. So this is the last few slides from the video. Just talking about general reactants, capital A, capital B. Using experimental data where there are 4 experiments, each with different concentrations of A and B, and different initial reaction rates, we can determine the reaction order with respect to each reactant and the rate constant for that reaction. So the rate is equal to the rate constant times the concentration of reactants to a certain power. So first we looked at the reaction order with respect to A. We're going to do a real example of this. So keep in mind the process of how we did this. To find the reaction order with respect to A, we need to determine if we change the concentration of A, how does that affect the rate? So we look for 2 experiments in our, we have 4 there, where the concentration of A is changing, but the concentration of the other reactant stays the same. So that way we know that if there was any change in the reaction rate, it's only due to the change in concentration of A. And that's how we determine the reaction order for A only. That's one calculation. Different calculation is determining reaction order with respect to B. And for this one, we choose 2 experiments where the concentration of B is changing, but the concentration of A stays the same. So that way, any change in the reaction rate will be a result of the change in concentration of B. After those 2 calculations, we have the complete rate law. We have the rate is equal to K times the concentration of A squared times the concentration of B. Once you have that rate law written out, then you can use any experiment row, any one row, to determine the value of the rate constant. So that would be the last part. That's a K here. All right, so that's what we did, or that's what I did at the end of the video. We're going to do that again, but for a reaction with real reactants, not just general A and B. So this is nitrogen, the formation of nitrogen dioxide. This is a component of photochemical smog. So if you think about smog in like California, I know there's a lot of smog in some areas. That can be formed through this reaction where nitrogen monoxide and oxygen gas react to form nitrogen dioxide. So we will use the data in this table. We have 3 experiments, different concentrations of nitrogen monoxide and oxygen, and different initial rates. We will determine the rate law, we'll determine the rate constant, and then the rate of the reaction for a specific concentration of nitrogen monoxide and O2. Before I move on and we start this question, do you all have questions about what was covered in the videos or what I just talked about? All right, are we ready? We're going to do it. Let's start with determining the rate law. So the rate law generally for any reaction is rate is equal to the rate constant, which we use lowercase k, times the concentration of each reactant, in this case that's nitrogen monoxide, to the power of its reaction order. We don't know what that is yet, so we're going to put an n there just as a variable. And then we do that for each reactant present. In this case, the only other reactant is O2, so concentration of O2. To, again, another variable, N and M is what we calculate when we determine the rate law. Okay, so let's start with N. To calculate the reaction order with respect to nitrogen monoxide, we need to find two experiments where the concentration of O2 stays the same, but the concentration of NO changes. We're going to compare reaction rates for those two experiments, and we want the change in reaction rate to only be due to change in concentration of NO. So looking at our options here, we can use experiments 2 and 3. Those two experiments, concentration of NO is doubled, concentration of O2 stays the same. So any change in the reaction rate is due to the change in the concentration of NO. So we will use rate of experiment 3 divided by rate of experiment 2. This is equal to the concentration of NO for experiment 3 divided by concentration of NO for experiment 2 to the power of N, and that N variable is what we're solving for. I explain in the video why we set it up this way. So if you're unsure about why I set up those two fractions with the exponent, definitely look back at that video. But we're essentially taking two rate laws and dividing them. All right, so now we can plug in values. Rate 3, 1.8 times 10 to the negative 4. Molarity per second. Rate 2, 4.4 times 10 to the negative 5 molarity per second. This is equal to concentration of NO for reaction 3.0042 molar. Divided by concentration for reactant 2.0021 molar to the power of N. Simplifying the left side is equal to 4, so the reaction rate quadrupled from experiment 2 to 3. Experiment 3 reaction rate is 4 times experiment 2 reaction rate. Within parentheses, that value is 2. So the concentration of A doubled, the reaction rate quadrupled. So this tells us the reaction is second order with respect to A. N, in this case, equals 2. We have to square 2 to equal 4. So the reaction is second order with respect to A. When NO doubles, the rate quadruples, so N is equal to 2. Yeah. Yeah, it should be 0, 1, 2, 3, 4, maybe. We probably won't ever see 5 or higher. And it will always be, should always be a whole number. So if you're not getting a whole number, that might indicate that something went wrong. Okay, so we have N. Now we need to calculate or do a calculation to solve for M. So the reaction order with respect to O2, oxygen gas. I'll use green here to calculate M. So we'll use similar setup, but we need to use information from two experiments where the concentration of A now stays the same, but not A, but NO stays the same. Concentration of O2 is what's changing. So for this one, we can use experiments 1 and 2. NO stays the same, O2 changes. So the rate for experiment 2 divided by the rate for experiment 1 is equal to concentration of oxygen for experiment 2 divided by the concentration of oxygen for experiment 1, all of that raised to the power of M. And again, we're solving for M. So getting to that point is important, and then after this, we're plugging in numbers and solving. So the rate for experiment 2, 4.4 times 10 to the negative 5 molarity per second. Rate 1, 8.8 times 10 to the negative 5 molarity per second. And then add in concentration values. Okay, so that point, we're just plugging in values. Now we solve left side of the equation is equal to 2. So the reaction, 1/2. The rate of reaction 1 is 2 times the rate of reaction or experiment 2. Then the right side is equal to 1/2 to the power of M. So in this case, when the concentration of oxygen is halved, the rate is halved. So both of these divide by 2. So that means that M is 1. The reaction is first order with respect to O2. Yeah. Okay, yeah, so if you look at these two experiments specifically, from rate 2 or reaction 2 to reaction 3, the concentration of NO doubled. So it went from 0.0021 to 0.0042. So that doubled, and that's why we get a 2 here. The reaction rate, as a result of doubling this concentration, increased by a factor of 4. And that's why we have a 4 here. So it's just explaining these two values here. And so that means that the N has to equal 2 for that one. So now that we've calculated N and M, we can write the rate law taking the same equation that I wrote at the top there. This rate for this reaction is equal to its rate constant times the concentration of NO squared times the concentration of O2. So this is the rate law And everything else on this page is the work that's required to determine the rate law. Other questions on this part? Okay, we'll go to the next question, or the next part of this question, which is to calculate K. Once you've written out the correct rate law, remember all this work is required first, then we have the rate law with the correct exponents. Then we can plug in concentration and rate data from any of the 4 experiments and solve for K. So I'll do that on the next slide. We need that rate law first to be able to do this, but we know just to rewrite that. Rate is K times NO squared times O2 concentration. And then just rearranging to solve for K. K is equal to the rate divided by concentration of NO squared times concentration of O2. So I'm just dividing both sides by those concentrations. Now, we can pick any experiment. I picked experiment 1. You could pick any experiment, plug in the values from that row, and solve for K. So using experiment 1, the rate is 8.8 times 10 to the negative 5 meters per second. I said meters like all class for my 9 a.m. Molarity per second, not meters. And then concentration of NO squared, 0.0021 molar squared, times concentration of O2, 0.0032 molar. And all of that is equal to K. The value on the left side of this equation is 6.2 times 10 to the 3rd power. But we need to think carefully about the units. In the fraction, we have molarity to the 1st power in the numerator. Then we'll have molarity squared times another molarity, so that's molarity cubed in the denominator. So 1 molarity, the top, cancels out with 1 in the bottom, and we're left with 2 in the denominator. And then the seconds to the negative 1st power, there's no other seconds unit, so that stays the same. So the units here, we have molarity times second to the negative 1st power in the numerator and molarity cubed in the denominator. This is equal to seconds to the negative 1st power in the numerator, molarity squared in the denominator. Or we can use a negative exponent for molarity. It's also equal to that, molarity to the negative 2nd power times seconds to the negative 1st power. Different reactions with different reaction orders will have different units for K. So it's important to include the proper units when you're doing these calculations. It depends on the individual reaction of what the units for K will be. So be careful with that. So we have 6.2 times 10 to the 3rd with our proper units. This is equal to K. Yes, go ahead. You can, like, that's not wrong. So the question was if you can use the S -1 over M2. It's not wrong. I think it's valuable and important to be able to see both, like understand both, because it might be easier to simplify with one versus another. So yeah, it won't be wrong. Like if it's a short answer question and those are your units, that's fine with me. But definitely understand both of them. All right, now, next question. Now that we have the rate law with the proper reaction orders, we have the value for K, we can calculate the rate for any concentration of the reactants, and that's what this question is. So you're determining the rate of the reaction when the concentration of NO is 0.0015 molar and O2 0.0024. This one is an iClicker, so I will get that started. And then if you've got questions about anything we've talked about, now's a good time also to ask. All right, maybe one more minute.
Don't worry about that. No, it's a book. Yeah.
All right, a few more seconds and I'll close it. All right, so we calculated the rate constant, we have the rate law, so now all we're doing is plugging in concentration values. So we use the rate law, which we determined after the first slide, add in the value for K, which we determined on the previous slide, 6.2 times 10 to the third, molarity to the negative second power, seconds to the negative first power. Then we put in concentration for NO, 0.0015 molar, and square it, and then concentration of O2. And the rate here is 3.3 times 10 to the negative fifth molarity per second. The rate should always be molarity per second, or I guess it could be grams per second if you're not working with concentrations. But it should be 1 unit of amount, so molarity, maybe grams, per second, or per some unit of time, hour, minute. If you have like molarity squared, then something went wrong either with your units for K or your rate law, so just keep that in mind. It should be amount per time. All right, questions on this? You have a bunch, not a bunch, but you have some of these to do for your Achieve. There'll likely be some on the assessment, so if you do have any questions, let me know. Yeah.
Well, I just don't you think like the Achieve questions are like really tough? Usually the questions are exams are not that tough.
Some of them are tougher, but that is okay with me. It's okay to like struggle with your homework. You've got your notes, and then yeah, on the assessment, generally the questions are not as tough as the toughest Achieve questions. But if you could do the toughest Achieve questions, then the assessment questions shouldn't be as bad. All right, let's go to the next section. So we're still talking about rate laws. The whole section, the whole chapter is about rate. But this section will consider how rate changes with changing time, which means changing amount of reactants. So we said that reactants are used up as the reaction proceeds, so as time goes on. And the rate of a reaction will slow down as the concentration of reactants decreases. So we'll have some integrated rate laws, which integrate time into the equation. Then we'll talk about half-lives, which is a specific rate of decreasing the amount of a reactant by 1/2. So far we've talked about how reaction rates decrease over time as the amount of reactant decreases. That degree to which the reaction rate is influenced by the concentration of the reactant is determined by the reactant order. So it depends on the reaction order. So we will learn about using these integrated versions of rate laws. So we'll be able to predict the concentration of reactant at a certain time, or use the concentration of a reactant to determine how much time has passed. That's what's used in like carbon dating. They can determine the half-life of carbon or some other element and identify how old some substance is, something that is discovered. All right, so we're going to talk about first order or second order reactions. This graph here we've seen in the first section. We have, or maybe the second one, but it was in the recorded video. If you have something that is zero order, the concentration of that reactant doesn't depend on how much is used up. It will just decrease at a steady rate. But something that's first or second order, the decrease in that reactant concentration is not linear. So that makes it difficult to predict how much of that reactant will be present after a certain amount of time. So we can use the integrated rate law to make that prediction. So in general, not integrated, but the first order rate law, if we think back to the first section, it was negative change in concentration of A, where A is some reactant, divided by change in time. So over time, change in concentration of A is going to decrease. That can give you information about the rate. More similar to what we just did in the previous section, the rate of this reaction would be K, so rate constant, times the concentration of A. It's first order, so that exponent is 1, and it's multiplied by the rate constant. The integrated rate law, this is derived in the book. I'm not going to go through the derivation. I'll write the equation out. It's provided on your equation sheet, and then if you're interested, want to better understand how this integrated rate law is derived from the first order rate law, you can definitely find that in the book. The integrated rate law takes into consideration time. So the reactant concentration at time that's not 0 seconds will be different, right, than the initial concentration. It gets used up, so the concentration decreases. So the integrated rate law is the natural log of the concentration of A at some time t divided by the initial concentration of A. And this is equal to negative K times time. So concentration of A with this subscript 0 is the initial concentration. Usually that's what's known. You know how much, a scientist would know how much, or if you're doing this experiment, you know how much of a reactant you're adding. And this is at the beginning of the reaction, so time is 0. 0 seconds, 0 minutes, whatever your unit of time is. Then concentration of A with that subscript T is the concentration of A at a different time. So 1 second, 40 seconds, 3 hours, some other time T. And that time is also part of this equation. We multiply it by negative K here. That integrated rate law can be rearranged into a y equals mx plus b. So the equation of a straight line with the slope m, constant b, and then we have y next variables. So we can rearrange this into a y equals mx plus b, and that is convenient for several reasons, but let's write out this equation first. This is natural log of A at time t is equal to negative K plus natural log of A at time 0. So remember, concentration of A at time 0, that is not a function of time. That is a constant value. A certain amount of the reactant is added. So this is the constant, which is referred to as B for y equals mx plus b. That's B, that's a constant, that's the concentration, or the natural log of the concentration at time 0. The time is what's changing. Time is changing, and the natural log, or the concentration of A, is a function of time. So depending on how much time has passed, concentration of A will change depending on that time. So time is x. Natural log of A at time t is y, and then negative k is the slope, or m. So this is the y equals mx plus b version of the integrated rate law. All right, this equation can be plotted on a graph and would result in a straight line where the slope is equal to negative k. So here we're plotting that integrated rate law, natural log of A at time t equals negative k times time plus the constant natural log of A at time 0. Okay, so now we'll talk about the half-life of a first order reaction. So this is when the concentration of A at time t is 1/2 the initial concentration. The time that passes, that's the half-life of that reaction, or that reactant for that reaction. So the half-life, or T with the subscript 1/2, the time it takes for 1/2 of the reactant to be used up. So if you look at this graph, it starts with 0.8 molar concentration, and a certain amount of time is passed before that reactant is now at 0.4 molar. So that's half of the initial concentration. And then the same amount of time passes for that reactant to go from 0.4 to 0.2. So halving again. And then same amount of time passes to go from 0.2 to 0.1. So that time, T1/2, is the half-life. So for a first order reaction, we have a equation for the half-life of that reaction. We'll start with the integrated rate law. So we're gonna, this right side will show how that formula is derived. So the integrated rate law, natural log of A at time t divided by natural log of A at time 0 is negative k times t. I don't have a lot of room on the right, but right above this graph, I'm going to show you that this fraction, natural log of A at time t divided by a initial concentration of A, if you place a negative symbol there, that's equal to the natural log of the inverse of that fraction. So we're going to use that in the next step. I'll move the negative to the other side. So if you're taking the natural log of a fraction, that's equal to the negative natural log of the inverse of that fraction. So we're going to use this in this next rearrangement where we can divide both sides by k. We're trying to solve for t. We'll divide by negative k and switch the numerator and denominator so that we don't have any negative sign in the equation. So we'll have k times the natural, 1 over k times the natural log of a at time 0. Notice that we inverted the fraction, divided by a at time t, and this is equal to time. We did that because we're looking for the half-life equation, which will start with the half-life, t of 1/2, that'll be equal to something, right? So we're getting t on its own, time on its own. At this point, we'll substitute the definition of A for a half-life, which is that the concentration of A at time t is 1/2 the initial concentration. So we can say this down here, A at time t is 1/2 A0. So we have 1 over k times the natural log of A at time 0 divided by 1/2 A at time 0, because that's what we mean by half-life. The concentration of A has decreased by 1/2. Now we can simplify here. We're taking the natural log of 1 over 1/2 because we can cancel out concentration of A at time 0. We get natural log of 2. So to simplify this last one, we've got natural log of 2 divided by k is the equation for the half-life for a first order reaction. So note here that the half-life for a first order reaction is independent of the initial concentration. There's no concentration of A in this equation. It only depends on K. And that's only for a first order reaction. We'll have a different equation for a second order. So, independent of concentration of A at time 0. Okay, we didn't get to the other iClickers, but we'll get to them tomorrow and I'll combine the 2 days. Do you have a question? Okay. All right, thanks everybody. Got more of this on Friday.
Are the iClickers still working?
Yes, but sorry, let me just end the recording.